Today we're going to talk about waves, and we're going to lay the foundation for what comes between now and final. And so today's going to be fairly basic because we need to understand the basics of waves before we can look at the exciting parts of waves. Like on Tuesday of next week, we'll talk about Mach cones and beats and the Doppler shift. And then when we come back from the holiday, we'll talk about standing waves, which is essentially music. Okay, we'll talk about standing waves on a string, something like a violin string, and standing waves in a pipe, like an organ pipe. And so that's where we're headed. And we're so close to the finish line. Folks, and I encourage you over the break, rest up, get find your strength to make it to that finish line. Would someone be willing to give us an opening prayer this morning? Someone that went, there we go. Thank you.
Dear kind and gracious Heavenly Father, we're so grateful for this day that we have to be able to learn and expand our minds more, to be able to progress in our pursuits, that we may be able to serve you and glorify your name and serve those around us. We ask the Heavenly Father that this day we may be able to learn and teach in efficient ways, to be able to help and serve those around us, to be able to go forth and become strengthened by this period, and we ask these things in the name of Jesus Christ. Amen.
Thank you. Okay, that of course was the theme song from Hawaii Five-0, from the original Hawaii Five-0, which came out when I was just a wee lad on the island of Guam. So this is a problem that is on your homework. And you remember we talked last day about this situation where the block bounces back and forth between these turnaround points. And we were told in this problem that the amplitude of the oscillation, that's the capital A, okay, that it was 16 centimeters. And that might be different for each one of you, but we're going to pick 16 centimeters. Now, we found that because this surface was frictionless, we didn't get robbed. And so the energy that we start with is always the energy we end up with. And that allows us to solve a lot of different problems. Now, the tools that we have are the energy equations. In general, I've got kinetic energy in the motion of the block, and I have potential energy in the spring when it's stretched or compressed. And that always applies. That's general. No matter whether it's here or here or here or here or here or here, always. But there are some special cases. At the turnaround points, you have to stop to turn around. And so in that case, the velocity is going to be 0, and this term will go away. Also, when you're at a turnaround point, this value of delta S, remember, what is delta S? Delta S is how far you are away from equilibrium, how far you are away from the length of the spring that it came from the factory with. Okay, and so it's either the stretch or the compression. Well, at the turnaround, this delta S has a very special value. It's A, okay? And is it positive A or negative A? I don't care, because it's squared, okay? I don't care. Now, in the middle, at equilibrium, the spring is neither stretched nor compressed. So at that point, at equilibrium, delta S is 0. It's not stretched, it's not compressed. And so there's no energy in this bucket. And so all of the energy is going to be in the kinetic energy bucket. And so that means that the speed is going to be the very fastest that it will be. Now, in this problem, the first thing you want to do, or any problem like it, and I promised you that there would be 2 of these on your final exam. The very first step is to find the total energy of the system. Even if you're not asked for that, even if you're not offered points for that, it's the piece that solves the puzzle. And so I know that the spring constant is 100 newtons for each meter. I know that the amplitude is 16 centimeters. I have to put that in meters. And so I asked myself, which of these equations is going to give me the total energy? Well, I've got K and I've got A. I'm going to use that formula right there. And that gives me 1.28 joules, a number that none of us really care about, except that that number allows me to answer all sorts of questions. I could say, well, what if the block is only 5 centimeters from equilibrium? How fast is it going? Or I could say, what if the block is going at 2 meters per second? How far is it from equilibrium?
Could you explain real quick why you did it with the second formula rather than the first?
Well, I could do it with the first one. I just plug in 0 there, and I plug in A, capital A for delta F.
I guess I'm asking why is it at the turnaround point? Does it matter what point it's at? The total energy?
You find the total energy with what information you have. If I had told you the mass of the block and the fastest speed, you would use this equation here. If I had told you when the block is 1 centimeter to the right of equilibrium, it's going 2 meters per second, you'd use this equation here. The general rule is by hook or by crook, whatever you need to do to find that total energy. In this case, I had K, I had A, boom. It just seems like the way to go. See how powerful that is? All sorts of questions can be answered as long as you know what that total energy is. Okay, let's try this problem. We've got a 2 kilogram block. It's at rest at the end of a horizontal spring with a mass constant of 100 newtons per meter. The block is pulled out 20 centimeters and released. What is the maximum velocity of the resulting oscillations? Okay, and again, we've got these formulas. The maximum potential energy is 1/2 Ka squared. Kinetic energy, we've known that for more than a month, 1/2 mv squared. With your neighbor, figure out what that is. What's the maximum velocity that this thing will travel?
I'm trying to figure out what my neighbor is. Now you're set. Potential energy running fast.
The first part of it.
Quantity should be. Just wanted to say. It didn't say cross energy. Did you find it? And you plug it in. Diameter box. For meditation. Like, how does it? Oh, yeah.
Okay, when you get an answer, use your clicker.
And then these. Makes sense.
So I didn't actually do the math.
Oh, yeah. Hey, where's Hannah? You have about a count. I mean, I'm not gonna deny that there's geniuses that exist in the world. You're not one of them. That's like. So good. I don't count.
That's good to know. Maybe I didn't know that, but then you did. You know, shut up. Like nature.
Yeah, it's. No, I didn't realize there's one I got actually today.
Okay, get your vote in. Make sure you get your attendance points. Okay, looks like A wins, and indeed that is the correct answer. Let's look at that. I can find the total energy because all of the energy is in the spring when it's at a turnaround point. And I'm told what the amplitude is, I'm told what K is, and if I plug in, I get 2 joules for the total energy. Now, the fastest velocity, remember that's what we're looking for, is when all of the energy is in the motion of the spring of the block. And since it was a 2 kilogram block, the math is really easy there. Essentially, I just have V squared is equal to 2, and that gives me 1.41 meters per second. So A was the correct answer. Check that your neighbor got A. If not, slap them good.
It looked like I'm also calling out.
Okay,
You holding. In case you're being.
these are the
I have a way to.
these are the key concepts from our last discussion, just to remind you where we've been. The period of oscillation, the time it takes for something to bounce up and down, depends only on the spring constant and on the mass. And that spring constant we can find in 2 different ways. The static method is we just hang it on a spring and see how much that stretches the spring. We use Hooke's law to find the spring constant. The dynamic method is we bounce that mass on the spring and we measure the period. And then we use our formula for the period of oscillation to solve for K. Sometimes we have enough information to use the static method. Sometimes we have enough information to use the dynamic method. Whenever we're looking for an acceleration, whether it's the acceleration at the turnaround point or the acceleration somewhere else, we always use Newton's second law. And the amplitude and the maximum velocity we just found with energy. Ha! Did you hear that back there in the back? Yeah. Did you smell my bad breath? No. Okay. The disturbance got all the way to the back. Their ears were assaulted just like your ears were assaulted. Your eardrums were pushed in and pulled out. And that's what a pulse is. It's a traveling disturbance that carries energy and momentum across the room. But the front row smelt my bad breath and you did not. And that's because this disturbance travels without taking the medium that's carrying it with it, without taking the air to the back of the room. Okay, there's no bulk motion of the medium. Essentially, as I shouted, what was happening is, if you think of the air, as you've been taught in high school, as a bunch of little tiny billiard balls so small that we can't see, atoms, molecules, essentially by shouting, ha, I was pushing those little bowling balls and they were bouncing into their neighbors and the neighbors were bouncing into their neighbors, and it just went across the room, much like gossip in a small town, okay? It just went from neighbor to neighbor until the disturbance got to the back of the room. Now, this idea of a pulse comes in two flavors. The first flavor is called longitudinal. And in this flavor, the bits of stuff that's carrying the pulse move parallel to the energy. And so that's going to be demonstrated by this hanging slinky here. If I pull one of these coils back, if I had a piece of yarn tied around that coil right there, what you would see as the pulse goes by is that that would be disturbed. But the disturbance would start back here and it moved across, okay? But if I look at any individual coil, you know, by tying a yarn around it, it's always moving away from equilibrium this way, parallel to the motion. Now I can simulate that with a computer image, and each of those arrows up there represent an equilibrium point for one of the coils of this slinky. Okay, and these dots represent the coils of the slinky. Or if you'd rather, they could each represent a bit of air, a molecule of air. And these are their equilibrium points. Now, when the dot gets the furthest from equilibrium it's going to get, I turn it blue just to help you visualize what's going on. So I disturb it on the left, and that disturbs the neighbor, and the neighbor, and the neighbor, and the neighbor, and the gossip is almost to you. You're about to hear about Aunt Marge. Okay? You see how the disturbance travels across, but the actual medium, this medium doesn't end up over there, just the disturbance. Now the second flavor we call transverse. And in that case, the bits of stuff that are carrying the pulse move away from equilibrium perpendicular or transverse to the motion of the energy. And an example of that would be this. This was first developed by Bell Laboratories many, many years ago, even before I was born. And Bell Laboratories used to be one of the big centers for research on acoustics. And for many, many years, Harvey Fletcher, a member of the church, who actually invented stereophonic sound, he was the director of Bell Labs for years. His son, Peter Fletcher, was the head of NASA when we went to the moon. And later, when the space shuttle exploded and we had that terrible tragedy, they brought Peter Fletcher back out of retirement to try to figure out what went wrong, because they trusted him so much. Peter's brother, Harvey Fletcher Jr., was my boss the summer after I graduated from BYU. And he was a mathematician, and we just worked ugly math problems all summer long. It was a miserable summer. That's not going to be on the exam. These rods are tied together right down the spine. there's a wire that goes right down the center, and each of these rods are welded to that wire. So that when I lift one of these rods through the torque exerted by that little thin wire, this rod is going to pull up its neighbor, and then this rod is going to pull up its neighbor. And watch what happens. I send a pulse, and it goes all the way down. But if I look at one individual rod, if I look at just that rod there, maybe by tying a piece of yarn to it, as the pulse goes by, the motion of that rod, it's not left or right, it's up or down. Okay, the energy is going from left to right, but each individual bit, the medium that's carrying the pulse, is going up and down, perpendicular to the energy. Again, we can visualize that. Each one of those dots now represents one of these rods, and when it gets furthest away from equilibrium, I'm going to turn it blue again, just to help you visualize where the energy is. Whoops, okay. Questions on those two different types of pulse? Okay. Now, in your tutorial this week, you're going to be exploring different pulses, but because this one is so much easier to visualize than this one, we're going to concentrate in the tutorial on transverse pulses on a spring.
So the transverse goes up and down, longitudinal is left to right.
I would rather that you memorize it differently, Josh. Transverse goes perpendicular to the energy, and longitudinal goes parallel to the energy. Okay, because I could have a wave that's going up, and I'm going to show an example of that in just a moment, in which case transverse would be left and right. Now, what we find, and again, the mathematics involved involves calculus, the solution to a differential equation. But what we find is that when a pulse is going down a string or a spring or a rope, a transverse pulse, it only depends on two things. It depends on the restoring force, the tension in the string or the rope or the chains, and the inertia. Now, if I've got two ropes and they're from the same factory, okay, and one of them is 1 mile long and one of them's 2 miles long, your gut tells you the 2 mile long rope is going to have twice the mass. But if I send a pulse down both of those ropes, it's going to be the same. The pulse doesn't know that one of them's longer. So it's not the total mass that matters, it's the mass per unit length. And we call that the linear mass density. And we give it the symbol mu, that's a Greek letter M. And this would be the total mass of the rope divided by the total length of the rope. And you see that that would be the same for both the 1 mile rope and the 2 mile rope. Okay, when I put in the numbers, the two cancels. Check with your neighbor, check with Nimrod.
Hey, Nimrod, is you okay?
Yeah, I'm good.
So basically, 2 miles. Build on it right here. The speed's gonna be the same.
Okay. Now, the formula,
Speed
and this is something that will be on the front page of your exam,
really.
and it's something that you'll be using in your homework that's due on Tuesday. You just take the square root of that tension and divide by the mass density. Now, a way of visualizing this pulse speed is if I think of the pulse traveling by having each piece of the medium get out of the way. Okay, in order for the pulse to go this way, those rods have to get out of the way to let it through. So think of a line of football players up here holding hands, okay? And they all had smiles on their faces until last weekend, okay? Do you understand what I mean? And if I wanted to send a pulse down this line of football players, we'd have them pulling on each other, and one of them jumps up, pulling his neighbor, who pulls his neighbor, who pulls his neighbor, who pulls his neighbor. How fast that energy is going to get down the line depends on two things. How hard it is to move one of those football players, and how hard they're pulling on each other. If instead we had a whole line of ballerinas, well, that'd go quick, you know, they're not as hard to get out of the way. So you can see that the mass matters, and also how hard they're pulling on each other. That would be the tension in the string or spring. Okay, now, sound, we just talked about that. That's a longitudinal pulse. That happens with these molecules going out and hitting their neighbors, and they go and hit their neighbors. And it turns out that that speed depends again on only two things. The average particle speed, which depends on the temperature of the particles and the mass of the particles. Now, I'm going to show you a formula that you will never, ever use in this class. And I would prefer that you not write it down, okay? What you want to write down is that what we find is that the speed of sound is 343 meters per second at room temperature, 20 degrees Celsius. And it gets faster if the room gets warmer, okay? As you start heating up the room, because each one of you represents a 75-watt heater, the room air gets warmer, and the lecture gets to your ears a little bit faster, okay? It turns out that it speeds up by 0.6 meters per second for every 1 degree that we raise the temperature in the room, 1 degree Celsius. Now, the formula that you'll never use is this one here, where that K is not the spring constant that we've been talking about. It's Boltzmann's constant, 1.38 times 10 to the negative 34. Anyway, it's not something that you're going to ever use unless you really go to the dark side and become a mad scientist, okay? The number you want is that one right there, 343, and that will be on the front page of the exam. Now, because the speed of sound depends on temperature, we get this concept called refraction. And that is on a, let's say it's a warm summer day. Let's go back to your youth, and your friends were on one side of the playground and you're over here. And it's a really, really warm day, and it's a blacktop, okay? And down here by the blacktop, the air is really warm, and up there higher it's cooler. Because this sound is moving faster than the sound up here, the energy actually moves up, it curves. And that's why when you were calling and saying, hey guys, come play with me, they pretended they couldn't hear you. Yeah, it wasn't that they were ignoring you, it was physics. Okay, let's go with that. On the other hand, when you're hunting in the winter time and the air is really, really cold next to the snow down here and warmer up there, any sound you make is going to bend right down to the elk, and they're gone. Okay, so that's the idea of refraction. Now here's that sample problem I was referring to a moment ago. We have a steel wire of mass 0.3 kilograms, and it has length of 60 centimeters, and it's supporting a 100-kilogram block as shown in the diagram. We pluck the wire in the midpoint, And that causes a small displacement. And we want to know how long does it take that displacement to reach the top of the wire? My first question is, why does that pulse go up instead of down? Talk to your neighbor. Why does it go up instead of down? Okay,
Thinking about this.
brave soul, do you have an answer for me? Yes,
Go both directions and you're just asking about one.
excellent. Say it louder, please.
Both directions.
It'd go both ways. Of course it would. If you throw a pebble into a pond, the disturbance goes out in every direction. It would go out as circles. Okay, and so I would have a pulse go up and a pulse go down. I was just asked about the one that went up. Okay, thank you. Now, how long will it take to get up there? Let's work that together. Well, if I want to know how long it takes for something to go somewhere, what I'm going to need is, oh, they're right in my pocket. Huh. I had them all along. We're going to need the speed. If you want to know how long it takes to get to Denver, you need to know how fast you're going. And that speed of the pulse was, remember, the square root of the tension force divided by the mass density. Now let's look at that tension force. If I draw a free body diagram for that mass, I have a weight force down. And that's going to be equal to the, it was 100 kilograms. So this is going to be 1,000 newtons. And this is just sitting there. So the tension by the wire on that mass is going to be 1,000 newtons. Now, you might argue that the tension is going to be a little bit bigger at the top of the wire than in the bottom of the wire. At the bottom of the wire, we're just supporting the 100 kilogram block. But at the top of the wire, we're supporting both the 100 kilogram block plus the wire. But notice that the mass of that wire is just 0.3 kilograms. And so that means that if I looked at that wire, at the bottom of the wire, the tension would be 1,000 newtons. And at the top of the wire, the tension would be 1,003 newtons. And folks, let's be clear. If you got a check in the mail that you weren't expecting, it doesn't matter whether it's $1,000 or $1,003. You're the same happy. You're exactly the same happy, right? Those numbers are so close to each other that we don't care. And that's the way these problems are. The mass of the wire is always going to be small compared to the mass of the block. So we can ignore it when we're looking at the tension. We can't ignore it when we're looking at the mass density, because that's the key point. Okay, so I'm going to plug in, for the tension, I'm going to plug in 1,000 newtons. Now let's look at the mass density. The mass density is going to be the mass of 0.3 kilograms divided by the total length of 0.6 meters. And that's going to be 1/2 kilogram per meter. So I put that in here. And that's going to give me about 45 meters per second, 44.7 meters per second. Now, if I want to know the time, I would use the equation for velocity, and that's just how far it travels divided by how long. And since I'm looking for how long, I'm gonna cross multiply here. So this is going to be a distance of 0.3 meters. Why did I use 0.3 instead of 0.6? Because it started in the middle. It only had to go halfway up. And then I divide that by 45 meters per second, and that's going to give me 0.0067 seconds. 45 meters per second is about 100 miles an hour. This thing is booking. Okay, so it's going to get to the top of that wire probably faster than you can blink. Questions on that problem? That's similar to some of your homework problems. Oh, yes.
The problem that the length of the wire is 0.6. So I'm confused why 0.3 is on top.
Oh, because we started in the middle and only went to the top. Yeah. We only have to go through half of the wire. Okay. Any other questions on? Okay.
Like that.
What about reflections? Watch what happens when this pulse reaches the end. It bounces back. Now, in the tutorial this week, you're going to explore what happens when it hits that boundary. And it depends on whether the boundary is free, like this one, or whether it is fixed. Sir, would you just hold on to that and keep it from moving? Okay. If I send that pulse again, now it comes down on the bottom. If you could let go, please. If I send it back now when it's free, it comes back on the top. And that's what you'll be exploring in this week's tutorial. Now, because our class has all of our tutorial sections today and tomorrow, we're going to go to tutorial. The afternoon class, they have their tutorials on Monday. And as you know, the Monday next week is really a Friday. Okay, so they're going to watch a video instead. But we get the real deal. Okay.
She'd actually say.
Question. What's different between these two groups? I've got a group on the left and a group on the right. And what you need to decide with your neighbor is, what is it about the group on the left that makes them a group? What's similar about them? And the same with the group on the right. And how is the group on the left different from the group on the right? So with your neighbor, give it a shot.
We're comparing each individual one. There's five of your other. I think you're moving. Like that. They're all moving on the right. Because the next set.
Okay, brave soul, raise your hand and share. Where are you, brave soul? Yes, sir. Oh, my goodness, I can't see you.
There's movement on the left column and no movement on the right column.
There's what?
Movement on the left column and no movement on the right column.
Okay. So something's moving on the left and nothing on the right. Okay, good. What else? Yes, sir.
On the left, they're all separated by the same time interval.
Okay. On the left, we're finding something that is repetitious in time, always the same interval of time. What about on the right? What about on the right? Anyone?
Separated in the same distance interval.
Okay, perfect. So on the left, we have a repetition in time, and on the right, we have a repetition in distance. If we think of telephone poles beside a long straight highway, you know, they're separated by the same number of meters as you go down that highway. And so the point I'm trying to make with this slide is that a wave is both. A wave is both. A wave results from a periodic disturbance. If I just disturb this once, I send a pulse. Okay, that's a single pulse. But if I disturb it over and over again in a periodic way, namely the same period, I send a wave. Okay, and it goes down just like a wave in the ocean. Now, it turns out that the wave always, every single time has the same frequency, the same timing as the disturbance that's causing it. And so we can characterize a wave by the amplitude. How high are those waves when they hit you as you come in from the ocean? That's the amplitude. How far do the bits, the water, move from their equilibrium? The period or frequency, how long does it take for each bit to go through one cycle would be the period. Now that seems very similar to simple harmonic motion, where we've been, where we were last day. Here's the new piece that we haven't seen yet, the wavelength. The wavelength is the distance over which this pattern repeats itself. So that would be from a crest to a crest, or a trough to a trough. And then the speed. It should not surprise you that since a wave is just a collection of pulses, whatever speed those pulses are going, that's also the speed of the wave. Okay, so the formulas that we came up with, the one for transverse pulses is also the formula for transverse waves. And if I have a, let's talk about sound. Ha! That would be a single pulse of sound. Ah, that would be a wave. That would be a lot of disturbances. Your eardrum was offended many times. Okay, not just once. Okay, but the speed of both of those would be 343 meters per second, the speed of sound. Now, it's a repetition in both space and time. Well, let's look at that. If I send a pulse, if I send a wave down this machine, and you take a picture with your camera at a point where it's going across, take it now, he took it, we get something like this. And what we see is that the amplitude is just the furthest those bits that are carrying the wave get away from the equilibrium position, either above or below. The wavelength is going to be from crest to crest, or from trough to trough, or in this case, in the picture, it's from equilibrium going up to equilibrium going up. Now, folks, I like to go from crest to crest or trough to trough. Why? Because if you go from equilibrium to equilibrium, you got to be careful, because you might go from equilibrium to equilibrium and only get half a wavelength. You got to repeat the pattern. This is equilibrium going up to equilibrium going up. But if you go crest to crest, you'll never make that mistake. Now, those wavelengths are often best thought about like boxcars on a train. Okay, if the boxcars are all the same length, we would think of each boxcar as a wavelength, and the wavelength is just how long the boxcar is. And so that tells us that the units of this lambda, that's the Greek letter L, well, it's a length, wavelength. So it has to be meters. And so counting boxcars is the same as counting waves. And we're going to make use of that in just a few moments here. Okay? Now, what if instead of taking a snapshot and freezing time, what if we instead freeze position by tying a little red ribbon around that rod right there and just concentrating on that ribbon? Ignore everything else, just that ribbon as the wave goes by. Well, as the wave goes by, that ribbon goes up, it goes down, it goes up, it goes down. And if I were to plot that as a function of time, I would see that it went up for a while, and then it went down for a while, and then it went up for a while, and then I got really bored with this, and I just didn't take very many points. Okay. But if I wasn't bored and I took 1,000,000 points, what I would find is that they would lie along a line that looks sinusoidal. Now, you remember from high school, that means it's either a sine wave or a cosine wave. In this case, it starts at 0, so it would be a sine wave. And it just follows this nice sinusoidal path. Now, again, the furthest it gets away from equilibrium, either up or down, is the amplitude, just like before with simple harmonic motion. And the distance in this axis, well, this is the time axis. So calling it a distance is really misleading. This is the period, the time it takes to go from crest to crest, or from trough to trough, or in this case, from equilibrium going up to equilibrium going up. Now, where on this graph would I find the wavelength? Where do you see the wavelength? You don't. Trick question. And that's why you need both. You need one graph with the repetition in space and another graph with the repetition in time. Okay, so in summary, if I take a snapshot and freeze time, I get the amplitude and the wavelength. If instead I follow a single point, essentially isolating a location, I get the amplitude and the period. And so what I get is the spatial repetition here and the temporal repetition, or the repetition in time, here. Yes, sir.
Still looking at a single point, or is it over the wavelength?
Here I'm looking at a single point. Here I'm looking at a single time. So this was the snapshot with the camera, and this is where I put the red ribbon on.
Not moving up there, but it's moving.
Okay. Now, let's check to see how well you understand. This comes from the textbook. You have a transverse wave going down a spring, and it's moving to the right. And we tie two little pieces of yarn, one at point A and one at point B. And what we have here is a snapshot right at noon. Took this picture right at noon. And the question is, if instead of a snapshot, I had taken a movie, how would A and B be moving in the movie at this time, at noon? My choices are A would be moving up and B down, A down and B up, C both down, D both up, A left and B right. Okay? Now, before we vote, let's just all agree that E is just silly talk, okay? Because this is a transverse wave. Nothing's going left or right except for the energy, the wave itself. But the bits that carry the wave are going up or down. So let's get in our vote. You can vote now.
Upstairs.
Like, it's don't, like,
A's already done, A's already done.
If you want to put down, but it hasn't.
And B has to go to the council.
No, P.
down and then.
No, I think you're tying a piece of yarn together. Like
This point.
to come out of the way. So it is in the.
It could be.
That-
Actually, it might be.
Same.
Okay, last call. Get your vote in.
Here where the.
Okay. Well, that's interesting. That's interesting. B is not the right answer, people. Let's talk about it. If this indeed were a movie, then the next frame would look like this. Because the wave's moving to the right. Now, the pieces of yarn have to stay on the spring. Okay, they have to stay on the spring because they're tied to the spring. Well, that means that A, if it's gonna stay on that spring and it can only move up or down, it's gotta move up to there and B has to move down to there. So A is moving up and B is moving down at noon when we took the picture. And so the answer would be A. Now, another way of thinking of this is that the pulse moves, the wave moves by the pieces of the machine getting out of the way. The medium that's carrying the wave gets out of the way. And if we look at B, it's still getting out of the way. Okay, this valley here is coming towards it and it's got to get out of the way so that the pulse can go through. Whereas the pulse has already gone past A, and so it's going back to equilibrium. It's going back to its happy place. Check with your neighbor. Make sure that your neighbor's okay with that.
Just move the wave to the right and then see the same point.
B was wrong and sick and wrong, both wrong and sick and wrong, okay? Slap yourself.
Yeah.
Because I can't do it. Yes, that's what they tell me. At orientation, that's one of the first things they told me. You cannot slap the students.
Obsess about it.
Okay, here's another multiple choice question. If the speed of a wave on a spring remains the same, but the wavelength is decreased, made smaller, what happens to the period of the wave? Does it increase, decrease, or stay the same? With your clicker,
B to the waist.
To make this. Sorry, man.
okay, go ahead and get your vote in. Last call. Okay, we don't really know, do we? We don't know. This is where it becomes very, very handy to think of those waves as trains and the boxcars as the wavelength. if I had two trains that were coming down the track and you were standing between them, okay? If both of those trains are going 30 miles an hour, which one are you going to have, which one would have the largest period? The period is the time it takes for a boxcar to go past. Well, if they're going the same speed, it's going to take longer for these boxcars to go past you than these cars. So if we are going to decrease the wavelength, that's the length of the boxcars, we're going to decrease the period. Okay, so the answer was B. Check to see if your neighbor put that answer.
I just had to move on to the.
Okay, in the first part of the class, we found that there was one equation that was more important, more useful than all the others. It was Newton's second law, F net equals ma. It seemed like over and over we were pulling that out of our toolbox. When we are dealing with waves, regardless of what kind of wave it is, whether it's a transverse wave, a longitudinal wave, a traveling wave, or a standing wave that we'll talk about after Thanksgiving, all kinds of waves follow one equation. We call it the wave equation. And I'm going to show you that equation right now. And it's very, very simple to understand. Imagine that you're at the beach and these waves are rolling in and you're standing there about up to here in the water. And every time one of those crests come, you kind of hop up on your tiptoes so that you don't drown, okay? So you're just hopping up every time one of those crests come. Let's say that those waves, the crests, are about 3 meters apart and that you're bouncing up on your tiptoes every 2 seconds. Well, how fast are those waves coming into the beach? Well, that's what it looks like. You're at point B and the waves are coming in towards the beach, okay? And you just bounced up to keep this crest from drowning you, and this crest is coming at you, okay? Well, how long is it going to take for that crest at A to get to you? 2 seconds. That's what we found. We're jumping up and down on our toes every 2 seconds. Well, how far did it move in those 2 seconds? 3 meters. So what's the speed? Well, I just take the 3 meters, divide by the 2 seconds, and I get 1.5 meters per second. What I did is I just divided the wavelength times the period. Do not write that down. Okay, do not write that down. Because that's not the form of the wave equation that we use. We know that the frequency of the wave is just 1 over the period. And so I can write this as the speed of the wave is just the wavelength, crest to crest, times the frequency, how many times per second we have a crest. That's the wave equation, the grand high wave equation, the one equation to rule them all and in the darkness bind them. Okay? That one needs to go into your toolbox right away because you're going to use that for your homework. Now I'm going to work a problem that is similar to one of your homework problems. This is a problem that's similar to problem 5 in the homework that's due next Tuesday. And when I say similar, what I really mean is the same. Okay, the same. So let's follow along here. We have a transverse wave, the amplitude of which is 1 centimeter. And a particle on the string that's carrying this wave moves a total distance of 12 centimeters up and down in 1/10 of a second. If the wavelength, the distance between crest and crest, is 1.5 meters, what is the speed of the wave? Okay? Now, in your homework problem, you're gonna be dealing with waves of water coming in and going up your leg and down your leg, up your leg and down your leg. It's the same thing. I've just dressed it up a different way. Okay, so let's visualize this. This is the wave traveling to the right on this string. And I've painted one little piece of the string orange. And we're going to find out how much that orange dot moves as one of these waves go past. Well, let's let it move. Okay, it's just moved a quarter of a wavelength, and that orange dot has moved from equilibrium down there. And how far did it move? Well, the amplitude of this wave is 1 centimeter. So it just moved from equilibrium to the amplitude, 1 centimeter. And then the wave moves further to the right, and this orange dot goes back to equilibrium. How far has it moved now? Well, one centimeter down, 1 centimeter up, it's moved 2 centimeters. But we haven't gone one wave yet. We've only gone half a wave. So now that orange dot goes from equilibrium to the top turnaround point. Now it's moved 3 centimeters. And now it goes back to equilibrium, and one wave has gone past, and the dot has moved 4 centimeters. Now you were told that that dot moves 12 centimeters in 1/10 of a second. Well, if every one wave is 4 centimeters of movement, how many wavelengths does it take to get 12 centimeters of movement? Shout it out. Yeah, 3. So what that tells me is that 3 wavelengths are going to move that dot to 12 centimeters, and that happens in 1/10 of a second. Okay, now, if 3 waves go past in 1/10 of a second, you remember what frequency is, right? Frequency is how many waves go past in a whole second. Well, if 3 can go past in 1/10 of a second, how many go past in a whole second? 30. So if 3 crests takes 1/10 of a second, how many crests in 1 second? That's 30, and that's the frequency. Now we're ready to solve the problem, because the speed of the wave is nothing more than the wavelength times the frequency. We were told the wavelength, that was given in the problem. That's 1.5 meters. And we just figured out that the frequency was 30 hertz, and hertz is just fancy for per second. And so what we get is 45 meters for each, or per second. Check on your neighbor, see if your neighbor got through that problem there.
I was trying to draw the thing that he was showing, like.
That was given in the problem. It
So
moves 12 centimeters in 1/10 of a second.
total. Sign county. Twice in one wavelength.
In general, and actually there's several problems in the homework that use this. In general,
You know that.
something has to move 4 times the amplitude when one wave goes past. If you start at equilibrium, it's got to go up to its amplitude. It's got to go down back to equilibrium. It's got to go down to its amplitude and back to equilibrium. That's 4 times the amplitude as one wave goes past. Okay? All right. Let's talk about sound waves. I'm sorry, there's a question?
You said in general, is there a time when that wouldn't be true?
What's that?
You said in general, that's the case, that wouldn't be true.
No, not on this planet, in this universe. No. I don't know about the universe where Spock has a beard. I don't know how things work there. Okay? We said that sound was a longitudinal wave. We can model that in much the same way we modeled a longitudinal pulse. pulse was just one disturbance. A wave would be a collection of disturbance that were traveling down. Now, if I look at a sound wave, I can model that with a pipe, and I've got air in the pipe, and I'm using a diaphragm here. That's just a speaker. Okay, a speaker has a diaphragm, and that diaphragm pushes air, and then it comes in, it pushes to the right, it goes back to the left. It goes from being like this, where it's compressing the air, to going like this, where it's causing a rarefaction or a low pressure region. And these disturbances of high pressure and high density move down the tube. Now, this is what it looks like. We call these places where they're bunched up, we call that a wavefront. That's the crest of the wave. That's the part of this, the analogous part to this transverse crest as it goes across. Now you can see that these crests, these wave fronts we call them, are traveling, and they would be going at 343 meters per second. I've slowed it down here so you can see it. But I want you to notice that if I just look at one molecule in this tube, it's not going very far. It's just going a little ways away from equilibrium. And if I look at a different one, it's just going a little ways from equilibrium. But the energy and the momentum is moving down the tube at 343 meters per second. Does that make sense? Now, because that sound requires those molecules to bounce into each other, we find that without the molecules, we don't have the sound. And I'm going to demonstrate that with this speaker here. Can you hear the speaker? I can't. Be grateful for your hearing, okay? It's going to go someday. I can't hear a thing there. Now, if I pump all the air out of that container, let's see what happens. Okay, I'm going to tap this off. Get rid of this sound. Can you hear it now? No one? Okay, I'm going to open it back up and let the air back in. Did the sound come back? In space, no one can hear you scream. That's the message, okay? That's the message. Okay. Are there questions so far? Okay. Thank you. It wasn't bothering me. One more idea. We've got 5 minutes. One more idea. And that is that as I set up this wave down this tube, what I find is that there are some places where I get a very big difference in pressure, and other places where the pressure stays pretty much average. And so we're going to look at this as it goes down. But I just want to first of all point out how amazing your ears are. I didn't say my ears, your ears are. Because for average sound, this amplitude is about 3/100ths of a Pascal. Now you remember that the pressure we live under is 101,000 pascals. And this teeny tiny fluctuation in the pressure is enough to make your eardrum go in and send sound to your brain. So this is very, very tiny, tiny pressure. Now, which molecules have moved in this picture? Well, here I've got a bunch of them close together, and here I have a bunch of them far apart. And so if I go back to my little representation with those molecules, and this time I'm going to send a wave instead of just a pulse. And when it gets to the furthest it's going to get to the right of the equilibrium, I'm going to turn it blue. When it gets the furthest it's going to get to the left of equilibrium, I'm going to turn it green. So watch what happens as it goes across. Okay. So you see right here, it's the furthest displaced it's going to be to the right. And here it's the furthest displaced it's going to be to the left. And so if I were to plot the displacement, how far it is away from equilibrium, here it would be the furthest it's going to get away on the right-hand side. And here it's the furthest it's going to get away on the left-hand side. But if instead I'm plotting, and a wavelength is just like it always is, from equilibrium to equilibrium. Now, if I were to plot where things are, where the pressure is high, well, let's look at that. Well, here they're all bunched up close to each other, okay? Here they're all bunched up, and here they're all bunched up. I was confused before. Here they're spread out, okay? And the average is in between. So it would be there and there. And so you see that where I have no displacement is where I either have high pressure or low pressure. And where I have the most displacement is where I have average pressure. Folks, there's a life lesson here. If you're not willing to budge, you're going to be in a place where there's high pressure. If you're willing to go with the flow, it'll be average pressure. Have a great weekend, folks. Good luck.